So hello, today's lesson we are going to continue on talking about extrema on extrema altogether, absolute extrema and relative extrema. So our focus really right now will be mainly on finding extrema on a closed interval. And what we have here are some guidelines for finding extrema on a closed interval. So you should have your notebook out, and I think you guys should write this down. It's not too difficult, but as with all these guidelines, it's good to have kind of something you can go back to. Since we are finding on a closed interval, you can be pretty confident that we are talking about absolute, or what's also known as global extrema. So to find extrema of a continuous function on a closed interval, again, key thing about a lot of this is continuous functions. On a closed interval from a to b, we're going to use the following steps. First, find the critical numbers of f in the open interval a to b. And I'm going to give you time now to write this down, and I will be scribbling it down also so that I know about how much time I should give you to write it down. And I'm not the quickest note taker by any means, so if I'm able to get this done, I think you guys can kind of keep up. If for some reason you guys fall pretty far behind, then you guys can have the substitute teacher or pause it for you so that you can kind of keep up. But I probably don't plan on giving you too much extra time on this video with the amount of material I would like to cover, so you won't be able to pause it very much, or you will not be able to finish this video, and you need to be able to finish everything that we do in this video. So, and I was writing as I talked here, multitasking, and so I'm ready to write down number one. I was just writing down all that stuff at the top. So step one is to find the critical numbers on the open interval. And remember, to find the critical numbers, we take the derivative and set it equal to 0. So then step two is to evaluate f at each critical number in AB. Now again, we are dealing with finding these absolute extrema on a closed interval when we don't have the graph. So it's very important to understand that too. Step three is to evaluate f at each endpoint, so at A and at B. So at each endpoint of the interval AB. So basically f of A and f of B. So and that's probably why, well, C, critical number, when we did these notes here, I can kind of go back quick here. When we were dealt with the critical number, we were talking about f of C, and we used C for that. C stands for critical number, but really what we've got going on here now is A being one endpoint and B being the other endpoint. And so you kind of have the why that's ABC kind of deal there. And then this is pretty kind of straightforward, but the least of the values is the minimum and the greatest is the maximum. So basically you only have to test all the critical numbers, and then you also have to test the endpoints, because the biggest value could be at an endpoint when you're dealing with a closed interval. And then again, that's why this is extreme. It says extrema up top, but really absolute extrema, or also known as, you should know kind of some double terminology here. If you're in a different textbook than the one we're using in class here, you would want to use the, you might have to say global. But absolute's used more often. Now, relative, the opposite, or well, not the opposite, but the other thing that textbooks use for that would be local. And so just kind of something to be aware of. All right, so example 3, what we're going to do here is we're going to locate the absolute extrema on the function on this closed interval from 0 to 4. And this is actually a pretty easy derivative to take, and so we'll see how we go here. But the derivative, f prime of x equals 3x squared minus 12. Now, it's very possible I'll make a mistake. Just hopefully I won't make a mistake, because no one is kind of double checking as I teach this to you. So we'll see. But that's the derivative, and then we set the derivative equal to 0, and then factor out. So I'm going to kind of do this in one step. Just factor out a 3. So we have x squared minus 4, and real quick, again, I'm not going to really show you all this factoring stuff that you should have learned in pre-calculus courses. So here, x equals 2 and negative 2 would be our critical numbers. But now if you look at our interval, actually let me use this. I like to use this one here. If you look at our interval, which is from 0 to 4, negative 2 is not on that interval from 0 to 4. So we actually don't even have to consider negative 2. So I'm going to cross that out. And so the only critical number we're concerned about are the critical numbers on the interval for finding the absolute extrema on that interval. And so now what I'm going to do is I'm going to evaluate each of these points into the original function. I'm going to evaluate each of these points. And so I evaluate 0, and this one's really easy, 0, and this goes into the original function, just be aware. Sometimes you have to think if something's going into the derivative or if it goes into the function. And we're finding the extrema of the function, and therefore we put it into the function. Well, anyway, f of 0 equals 0. So let's do the critical number. I like to kind of do the first endpoint, then all the critical numbers on the interval in order, and then the final endpoint. Just kind of, you can do them in any order you want, but kind of works best that way, I feel. And so what we get here is 2 cubed, which is 8, minus 12 times 2, which is 24. And so then 8 minus 24 is negative 16. And then f of 4, so we're going to plug in 4. So we have 4 cubed minus 12 times 4. 4 cubed, 4 times 4 is 16, times another 4 is 64, minus 12 times 4 is 48. And so what we get then is 64 minus 48, which is going to be 16. And so what does this mean? We need to kind of write our answer out of what this means. And so this is kind of our answer. The function has an absolute, spelling will probably come into factor when you're not here too. Just kidding. Absolute, and we're going to go with, let's go with the maximum first. And you can actually give an ordered pair here because you've already figured it out. And the biggest of these numbers, let me use the magic pen again, the biggest of these numbers was 16. So our absolute maximum will be at 4, 16. And we can use a pronoun since it goes back to the function now, has an absolute minimum at, and the lowest of these is, hold on, negative 16. That's the lowest of these. And so the least of these values. And so therefore, what we can do then is say it has it at 2, negative 16. And then we should just kind of add, because we're only dealing with the interval from 0 to 4. That's all we care about. And I think it's worth kind of visualizing this on the graph. So I'm going to bring up the graphing calculator. And in the graphing calculator, I'm going to take and plug in this function, which is x cubed minus 12x. Operating system. All right, minus 12x. And now, really, the window we're only concerned about is from 0 to 4. So if you want, you could just kind of go from 0 to 4. But then you're kind of missing the endpoints a little bit. Maybe not. Let's go from 0 to 4. And we also could go scale. Let's just go by 1. But we already know what the minimum is. It's negative 16. So let's go a little further and go negative 20. And we know the maximum is 16, so let's go 20 there. Let's go y scale just by 5. The scale really doesn't matter, just how many tick marks, and it's easier to see then. And so when we hit graph, there's our function. And so if I hit second calculate, and I find the value, you could just kind of check it this way. The value at x equals, let's say, well, let's just kind of do the endpoint first. 4, you can see that that's the point 16, and there you go. That's the highest point, and you can kind of see it's the highest point. And now you've already learned how to do this probably in pre-calculus, but you can hit second calculate, and you could actually use your calculator, use the minimum value, number 3 here, and then go left bound. You got to go left of where the lowest spot is. And to be sure about this is taking a while to arrow over, but you want to just make sure you're for sure to the left. So I'm going to go to the little tick thing goes up a little bit. I've hit it way too many times. All right, you don't have to go that far. All right, so let's just kind of come back a little bit here, and then I just want to make sure I for sure go beyond the other one, and I go up a little bit. All right, hit enter, and hit enter again, and guess. And see, there's some round off error on your calculator, but you can see, because, other than the round off error, that this is x equals 2. Pretty much, you could be pretty confident with this. That's the problem with the calculator. But nonetheless, 2 negative 16 was the lowest spot. Now, I show you this on the calculator, and you're thinking, well, can't we just do this on the calculator? Well, this is calculus class, and you can probably be pretty confident that, not the quiz on this Friday, but your following quiz that I give you, which will cover this first section, you will not be able to use a calculator. And I guess just be aware of that. You might have some issues like 4 to the third power here I had to do, which is 64. But beyond that, I could maybe give you a calculator that's not graphing also, but we'll see. I don't even have enough for everyone in the class, so you should be able to do that kind of arithmetic anyway. All right, next problem. We're going to do kind of the same thing. We're going to locate the absolute extrema on this function on the closed interval. One thing to be aware of, we got f of t equals t over t minus 2. It is kind of important to understand your domain here. Your domain would not include t equals 2. But we do not have to worry about t equals 2 because t equals 2 is not on this interval here. We're only concerned about from the interval from t equals 3 to t equals 5, including t equals 3 and including t equals 5. And so, without further ado, that was something good to talk about the domain. We're going to take the derivative. Step 1, we need to find the critical numbers. And critical numbers are when the derivative does not exist, the function is not differentiable, or critical numbers occur when the derivative is equal to 0. So we take the derivative and pretty much use a quotient rule here. You could rearrange it so you have to use a product, but that's just not great because then you're dealing with negative exponents so much. And this one's not that hard to do as a quotient rule. So derivative of the top is 1 times the bottom is t minus 2 minus, don't forget it's subtraction there in the quotient rule, derivative of the bottom, which is 1, times the top. See how nice that is? All over the bottom, t minus 2 squared. Now we're going to simplify this before we set it equal to 0. Actually, I've been doing that in the same step here, so let's do that in the same step. So set it equal to 0, but simplify. And so in the numerator, we've got 1 times t minus 1 times t. So this t cancels with this t if you're looking at it. Actually, this whole thing. So all we have is a negative 2 in the numerator. In the denominator, what do we have? Well, we've got t minus 2 squared. And so our only critical number would be t is when the denominator equals 0, because that's when our derivative would not exist. Well, that also was not on our interval. So yes, t equals 2 is a critical number, but it's not on our interval, so we're going to ignore it. And so because the numerator doesn't have a variable anymore because it canceled out, this works out real nicely, and we don't have any critical numbers. Does that mean we have no extrema? No. We still have extrema. And what we need to do to test for the extrema are just the endpoints. So 1 will be our minimum, 1 will be our maximum. So what we've got then is we just plug it in. h of 3. h of 3 is 3 over 3 minus 2, which is 3. And we have h of 5. And h of 5 would be 5 over 5 minus 2, which is 5 over 3, 5/3, just 5/3. And so there you go. And this function, here comes our answer, has a n, sorry, absolute, let's go with maximum first. Doesn't matter the order you say them. At maximum, the highest number is 3. 5/3 is smaller than 3. So at 3 comma 3. And an absolute minimum at 5 comma 5/3. And we should just say on the interval from 3 to 5 because it has other extrema, and it's important to understand that interval. So that is a great answer, kind of written out, exactly explaining what's going on, and you need to kind of get in the habit of doing that. So this section, this whole chapter, applications of derivatives, is huge on understanding calculus. And so to explain that you understand calculus, you need to write them out. Don't just kind of slop stuff down. So interpret it using kind of the note, do a lot of the showing the work, but then interpret it. Again, we could check our answer here. I think this one's probably worth checking. With the new operating system, we can kind of type this in. Of course, remember this is t, h of t, so we're not really dealing with y's and x's, but we can just interpret it with an y and an x for the purpose that we need here. And then window, we're just looking from 3 to 5. And you'll see that this is always increasing or always decreasing, and that's something we'll talk about later in this section, or in this chapter. Let's go from 0 to 5. Well, 5 was our, oh no, 3 was our biggest number. 5 will work, and let's go by 1 again here. And so you can kind of see that, oh, look, it's always decreasing. And if you really want to check, you could just calculate the value. Don't do that minimum, maximum thing now because we're doing the endpoints and it won't work correctly. Trust me on that. So if we check the x equals 3, you get 3, which we talked about. 3 was the maximum. And if I hit second, calculate, and then find the value at 5, you'll see that we get 1.6 repeating, which is 5/3. And so those were our 2 points. And you can kind of check it there and use your calculator to check your answers like on homework. But again, you need to be able to do this without a calculator. All right. Next example. Locate the absolute extrema of the function on the closed interval. Trigonometry. We had a fun discussion about this yesterday. So let's just take one step at a time, and let's find the derivative of secant x. Oh, I'm sorry, I started writing. Oh, yeah, that would work. What's the derivative of secant x? Well, it's going to be secant x times tangent x. All right? And then we set this equal to 0. Well, let's look at this. Secant is, and let's just change everything into sine and cosine because I think it's easier to interpret in that format. And so, and we could change the original back too. But secant is 1 over cosine. So it's 1 over cosine x. And tangent x would be sine x over cosine x. And so this would be all equal to the sine of x over cosine squared x. Now, let's talk about this some more. Just kind of getting a graph here, and this will be my little sine and cosine graph. Here is my cosine. Let's talk about cosine first. Okay? Our cosine graph crosses here at pi over 2. It gets down here at -1. This is -1. This is +1. This is at pi, and comes back up to 1 at pi, 2 pi. Oh, and it crosses here, sorry, at 3 pi over 2. Well, technically, I didn't have to put all that information on there because we're only concerned about from -pi over 6 to pi over 3. Well, I do have to get in the negative realm, though, don't I? Okay, well, -pi over 6 is like right here. This is -pi over 6. And pi over 3 is like right here, pi over 3. So one thing to be aware of, and I hope you're kind of catching this, for the secant function, secant is equal to, so secant x is equal to 1 over cosine x. Well, we're going to have issues when cosine x is 0 because secant, that would be dividing by 0. But if you look here, and let me use the magic marker again here, that only occurs right there, and that is outside our interval. So on our interval here, from, and this is the other thing a magic marker could do. So from our interval from here to here, this function cosine x, and this is cosine x, doesn't equal 0. So we never have an issue with secant x being undefined. Understand, secant x is never equal to 0. Secant x is never equal to 0. So that's kind of a good thing to know too. So this is, again, let's go with y equals cosine x. And that's just cosine x. All right. Now let me use my blue marker and do the best I can do with sine x. It will look something like this. Oops, missed that. Missed the mark there a little bit. But again, we don't really care about that on the right. So this is y equals sine x. And why did I graph that? Well, considering the fact that cosine x is never 0 on our interval. Again, a big thing to look at is the interval in question. So a big thing is to look at this interval. But sine x is never equal to, or sorry, cosine x is never equal to 0. So the denominator here will never be 0. So all we're really concerned about is when sine x equals 0. And sine x equals 0, this one you should know, because sine x is the one that crosses at the origin. So our only critical number is when x equals 0. That's our only critical number, and that's on the interval. So we have one critical number that's on the interval, and it's x equals 0. All right. So yeah, all right. So now what we want to do here is just take the original function and evaluate them all. This will be fun. We want to evaluate all of them at, sorry, thinking, not speaking really right now, at the endpoints and at 0. All right, so secant x. Secant x is 1 over cosine, or sorry, secant is 1 over cosine. So this is the same as 1 over cosine of negative pi over 6. And so this is where you guys, I know you have some issues with this, but look back at the graph of cosine x, because if you can switch everything into sine and cosine, you can figure this all out. And then just remember that you're going uphill, downhill. And so negative pi over 6 is going to be this spot, which is really close to 1. Now 1 is the square root of 4 over 2. And if you go back one step on the trig function, this right here is going to be the square root of 3 over 2. Is it positive or negative? Now that's where you could look at the quadrants and go, all students take calculus, and understand that negative pi over 6 would be right here, looking at the unit circle. So yeah, cosine, which is why the C is here, is positive. So cosine is positive. But you really don't have to even look at that, because you could look at the graph up here, magic marker, the graph up here, and understand that it is up in the positive realm. Okay? Now, it didn't make that work, though, because it disappeared. So what we get then is when we're trying to find the secant of negative pi over 6 without using a calculator and knowing this stuff, because I kind of mentioned that you're not going to use a calculator too, didn't I? Is you realize that this is 1 over the square root of 3 over 2, which would be the same as, kind of running out of room here, 2 over the square root of 3. And if you remember rationalizing the denominator, which we haven't done a whole lot in this class, but with these trig functions you have, you'd multiply top and bottom by the square root of 3. So it's 2 times the square root of 3 over 3. So that is the value of g of negative pi over 6. So now we need to find g of 0. G of 0 is going to be the secant of 0. This one's pretty straightforward. Remember, again, it's 1 over cosine 0. And cosine of 0 and sine of 0 you probably should know again. Just kind of things you should know. And if you look here, that right there is the location, because that's the cosine graph. Let's travel along the cosine. Oh, that made it bigger. Let's travel. That's not what I wanted to do. Let's travel along the cosine graph. Okay, there's the cosine graph. Well, there's cosine of 0, because that's when x is 0. So cosine of 0 is 1. So all you get here is 1 over 1. 1 over 1, that's going to disappear. So I got the wrong marker. I'll come back with it. 1 over 1, which is 1. So the secant of 0 is 1. All right, and secant of 0, this might be a little confusing. Is that bigger or smaller than 2 times the square root of 3 over 3? Well, look backwards and think of it this way. 2 over the square root of 4, and square root of 4 is bigger than square root of 3, would be the same as 2 over 2, which is 1. And so that right here, 1 is going to be bigger. 1, this is bigger than g of negative pi over 6. So this is the biggest so far, and this is the smallest up here so far. But I say so far because we still have to evaluate, let's delete this, we still have to evaluate secant of pi over 3. So, boom, so g of pi over 3. So we get the secant of pi over 3, which is the same. I mean, you can figure out the secant of pi over 3, and some of those maybe you should actually memorize. But I'm just trying to help you here and telling you that you can change it into cosine of pi over 3 if you can't remember. And then you look here and say, oh, pi over 3, cosine. All right, so let's see this little dot traveling along. Actually, I'm going to make it, oh, I already have a dot up there. I can just take this dot and travel it along. So I got this dot, oh, it's kind of attached to something. So let's, well, I'll just take the magic marker here. So we're here at 1, and as we travel down, here is pi over 3. We're still in the positive realm, but we've gone quite a distance. And these go, value-wise, for the y, they go at a value of these radicals of numbers over 2. And so, basically, this is what I'm trying to explain to you, and maybe I'm just missing the mark here. Let me get the right pen. But here, this spot is the square root of 3 over 2 for y. And this spot here is the square root of 2 over 2. Oh, that's nice, square root of 2 over 2. And so this last one, which would be pi over 3, the cosine of pi over 3 is square root of 1 over 2, which is 1/2. And so, scrolling down here, this is nothing more than 1 over 1/2, which is equal to 2. So, guess I get to erase which one's the biggest and reevaluate which one actually is the biggest. The biggest is 2. 2 is the biggest one here. So it ends up being that the endpoints, yeah, we had a critical number in the middle there, but the endpoints are our extrema. And there's reasons for that. Reasons for that, just kind of understanding, is if we go back to yesterday, just kind of quickly looking at y equals x cubed, we have a critical number at the origin, but it's not a minimum or a maximum. So we're going to learn what that's actually called. It's like it's actually called a saddle point. And so that's called a saddle point because it evens out and your slope of your tangent line is 0, but yet it's not an extrema at all. So anyway, back to this. Here's our answer. The function has a relative, sorry, I spelled again, foiled, relative maximum at, and the highest point with this last one, pi over 3, comma, oh, not 3, 2. And it has a relative minimum at, and the other one was negative pi over 6, 2, okay, so this will be kind of fun. Negative pi over 6, comma, not negative, 2 times the square root of 3 over 3. That's the location. And this is all on the interval from negative pi over 6 to pi over 3. on that interval, and that's a closed interval. So that's your answer. I think it's important for us to right now to do what we did with the last ones and just kind of graph it real quick so you can visualize it now. So a couple things when we're dealing with trig functions is to make sure that you are in radian mode, and we are. So we go here, and the other thing is you can't type in secant theta, or secant x, I mean, and so what we'll have to do is just go 1 divided by cosine x, not a big deal. And then let's change our window. Our minimum value is negative pi divided by 6, and you can actually type that in there, negative pi over 6. And then our maximum value was pi divided by 3. So those are our endpoints. What should our scale be? Let's go pi divided by 2, which is a common scale for trig functions. And then our y-min, what was the smallest value we had? Let's stick with 0 for now, and our biggest value was 2, so let's just go to 3. And then we'll go by 1 there. So those are normally decent numbers. So we graph this, and you can see that I made a mistake. I had this feeling I made a mistake. So negative pi. So I guess what they're saying, what we did wrong here is something with negative pi over 6. So let me just kind of double check here. Yeah, secant is that. That is 1 over. So 1 over pi over 6 is cosine. And so we get 1 over the square root of 3 over 2. That's right. It's less than 1. Oh, but yeah, 1 over something less than 1 is going to be bigger than 1. Why did I think this was bigger than 1? Because, oh my goodness. I feel bad now. It happens. My logic was incorrect. Let me explain. So my logic here is if we had this, then that would be a bigger number and would be equal to 1. But if the denominator gets bigger, you actually get a smaller number. So my bad. This number here, and we could check this. If you didn't, I was trying to do it without a calculator, but we could check this. If you do 2 divided by the square root of 3, this is not smaller than 1. That's bigger than 1. Oh, double it up. So my bad. The smallest value actually was, I always make mistakes, don't I? So anyway, the smallest value was this one. This was the least of the values is 1, because this was approximately, you saw, 1.16. And so the biggest one is still 2. The smallest is 1. So now I just have to fix my answer here. Eraser. My minimum was not here. My minimum was at 0, 1. Actually, kind of easy to write. 0, 1. And so coming back, let's double check this. Back to the graph. If I hit second calculate value of pi divided by 3, this should be 2, right? All right, what happened there? I think I know what happened. I think it's on the edge of my graph here. So let me second calculate value pi divided by 3. Yeah. So it's on the edge of my graph. And so let me just kind of do a window here. And then so do my max. My x max, I'm going to do pi divided by 3 plus 0.1. I'm just going to do it that way. So I for sure can get this value. So I hit second calculate value, and then I do pi divided by 3, and it's 2. Look at that. I just added a little 0.1, which actually added quite a bit there. And then second calculate, and now the other one we could do is the minimum. And here's a quick way. I forgot, this is a quick way to kind of move your cursor. Go negative 0.1, enter, and then you could, oh, I hit it too many times. Clear. Second, calculate minimum. I'm already there. Now this arrow over, hit here, here, and there it goes. it looks like y equals 1 if you're looking at it, but this minimum, the first x value, it looks like 1.5, but look at that. It's e to negative 6, which means times 10 to the negative 6, which is basically 0. 0, 1 is the answer there. All right. I want to go through one more example and then give you your homework. So this one is from your textbook. So you could get out your textbook, and we are on page 167. Page 167. Should have had this up before. And we're going to do number 58. And this one isn't too bad at all. Let me see if I could take a picture here for you. This will be interesting. I've never kind of used the hover cam. Well, I kind of used the hover cam, but not. All right. And set this up. I should have had this set up for you. I apologize. So that's not very visible. That's worse yet. All right. Well, you can see it in your textbook. So let me see here. Wrong one. Too many tools going on in the bottom of my screen. All right. So it says inventory cost and good. So it says inventory cost. All right, inventory costs. A retailer has determined that the cost C of ordering and storing X, I can't read that, X units of a certain product is C equals 2X plus 300,000 over X. And the interval is from 1 to 300. The delivery truck can make at most 300 units per order. That's why the interval's like that, but you actually have to make some unit. That's why 1's the smallest. Find the order size that will minimize the cost. All right, so to minimize the cost, we want to find the minimum value of this function here. So basically, we have C equals 2X plus, let's rewrite this as 300,000 times X to the negative first. And we're going to take the derivative of this. So I'm just going to go big C prime. 2 plus, well, it ends up being negative 1 times 300,000 times x to the negative second. So then I set this equal to 0. So 2 minus 300,000 over x squared. Moving things to other sides of the equation, I get 300,000. I'd move this because it's negative over x squared equals 2. Multiply both sides by x squared. 300,000 equals 2x squared. Good. And divide both sides by 2. So we have 150,000 equals x squared. And so x equals the square root, and I know it's plus or minus, but you can't have negative units. So we have the square root of 1,500. And as you will see, this is not on our interval. I'm just going to double check that I did things right. Boom, boom, boom. Take the derivative. Boom, boom, boom. Looks good to me. And so this is not on our interval. So I have x is approximately 387 units. But as you can see, our maximum on our interval is 300. So let me just pause this for a second. Where is my thing? I've done this before. Sound, hardware, can't find recording. All right. So let me just pause this for a second. Yep, here we go. I paused it. I'm back. Yeah, so we did everything right. It just seems weird. And so what it says here is that this is outside the interval. And so what is minimized? Well, what's going to be minimized when you plug in these values? If you plug in 1, the cost is going to be, figure it out real quick. This is how much it's going to cost if you have 1 unit. And so then you have to test the other point, so C of 1. And so then you do C of, obviously the more units, the better. It would be best if we could ship 387 units according to this function, but we can't. And so what we got now is 600 plus 300,000 divided by 300. And so adding this up quickly is, well, dividing it here, is 600 plus 0, 0 cancels, 1,000. So this will actually minimize our cost to just $1,600 per unit, which is the cheapest we can do. I think it's dollars per unit there, if you want to look quick. So to minimize cost, we could, if we had a bigger truck that used the same function, 387 units would be our minimum cost, but our minimum cost is 1,600, or well, that's how much it'll cost, but 300 units. Now, if you're reading here, you can't see it. Now it says, could the cost be decreased if the truck were replaced with one that could bring at most 200, 400 units? And the answer is yes, because that would be our minimum cost when the truck carries 387 units. All right, so sorry about the mistake earlier and a little confusion here, just kind of double checking everything. This got a little sloppy, this problem. Hopefully you followed that. I can explain it a little bit more to you later. This is the homework that I want you to do, and this will be due then. Tomorrow you need to get the study guide done, so get that done for tomorrow, and then we'll have the quiz on Friday, so this won't be due till Monday. We don't have school Monday, so this will be due Tuesday. And that would be the lesson here, and looking at the time here, hopefully you started right away. You guys, have a great day.